Welcome to the deep dive. Today we're going really small, to the edge of the very, very small,
Oh,
to explore a concept that might just leave you questioning the nature of reality.
okay.
The Planck length.
Right.
You've shared some material that dives into this fascinating topic,
Yes.
and I'm really excited to unpack it all with our expert.
It's a pleasure to be here.
Mm.
The Planck length really is a mind-boggling concept, and I'm always thrilled to delve into its implications.
So let's start with the basics.
Sure.
For our listener who might be encountering this for the first time,
Yeah.
can you give us a plain language explanation of what the Planck length is
Okay.
and why it matters so much in physics?
Absolutely. The Planck length is essentially the smallest possible meaningful distance in the universe.
Okay.
Think of it as the ultimate limit of measurement,
Okay.
a point beyond which our current understanding of physics starts to get a little fuzzy.
I see.
To give you an idea of just how tiny we're talking,
Yeah.
imagine the size of an atom. Compared to the entire observable universe,
Yeah.
that's about the same scale difference
Okay.
as the Planck length compared to that atom.
Wow. That really puts things in perspective. It's hard to even fathom something that small.
Yeah.
But why is this tiny length so important? What happens at the Planck scale that makes it so special?
That's where things get really interesting.
Okay.
You see, in our everyday world,
Yeah.
the laws of physics, as described by classical mechanics, work beautifully.
Right.
They explain everything from the motion of planets
Mhm.
to the trajectory of a baseball.
Right.
But when we zoom in to the subatomic realm,
Okay.
a whole new set of rules takes over. Quantum mechanics.
Okay, so I've got these two sets of rules. Classical physics for the big stuff and quantum mechanics for the tiny stuff.
Right.
But it sounds like the Planck length is where these two worlds collide, right?
You hit the nail on the head.
Okay.
The Planck length is thought to be the scale where the effects of quantum gravity, the elusive theory that seeks to unify quantum mechanics and general relativity,
Okay.
Einstein's theory of gravity,
Okay.
becomes significant.
Now, you mentioned quantum gravity. I've heard that term thrown around, but to be honest, I'm not entirely sure what it means. Can you break it down for us? What's the big deal about unifying quantum mechanics and gravity?
It's a big deal because right now, these two pillars of modern physics seem to be speaking different languages.
Oh,
Quantum mechanics describes the behavior of particles and energy at the subatomic level,
right.
where everything is probabilistic and uncertain.
Okay.
General relativity, on the other hand,
Right.
governs the large-scale structure of the universe,
Mm-hmm.
explaining gravity as the curvature of space-time caused by mass and energy.
So they're both incredibly successful in their own domains.
Yeah,
But when we try to put them together, it's like trying to fit square pegs into round holes.
that's a great analogy. The math just doesn't quite work,
Okay.
and that's where quantum gravity comes in.
Right.
It's the quest to find a single, overarching framework. Right.
That can encompass both the bizarre world of quantum mechanics and the smooth geometric realm of general relativity.
And the Planck length is crucial to this quest because it's the scale where we expect these two forces to really show their interconnectedness.
Precisely. At the Planck scale, the quantum nature of gravity, which is usually negligible at larger scales,
Right.
is thought to become so dominant that it can no longer be ignored.
Okay, so we're talking about a realm where the very fabric of space and time might behave in ways we can barely comprehend. It makes me wonder, is there some sort of transition as we approach this Planck length threshold? Does classical physics just suddenly stop working, or is it more nuanced than that?
You've raised a great point.
Okay.
And thankfully, it's probably not an abrupt, jarring shift.
Okay.
Think about zooming in on a digital photograph.
Okay.
At first, you see smooth curves and continuous lines.
Yeah.
But as you zoom in further,
Yeah.
you eventually hit the pixel level.
Oh.
And the smooth image breaks down into individual blocks of color. So as we approach the Planck length, are we essentially zooming into the pixel level of the universe? Does reality itself become pixelated?
That's a good way to visualize it, though. Not literally pixelated in the way a digital image is.
Okay.
It's more that the smooth, continuous picture provided by classical physics starts to break down.
Okay.
The familiar laws we rely on might no longer apply in the same way. Instead, the quantum world takes center stage.
Okay.
It's not that classical physics stops working,
Right.
but it becomes inadequate to describe what's happening at such incredibly small scales.
So quantum mechanics provides a different set of rules,
Exactly.
a different framework that's better suited to explaining what's happening at this pixel level of reality.
Exactly. And that's where things get really exciting.
That is exciting. But if both classical physics and quantum mechanics are part of the same universe, there must be some way to connect them. How does one transition into the other, and what role does gravity play in all of this?
That's the million-dollar question that has been puzzling physicists for decades.
Oh,
The interplay between quantum mechanics and gravity is one of the biggest mysteries in modern physics.
okay.
We know they both exist, and they must be connected somehow,
Right.
but finding a unified theory has proven incredibly challenging.
Okay.
It's like trying to translate between two languages that have some similarities, but also fundamental differences in their grammar and structure.
So we've got these two separate rule books,
Right.
one for the big stuff,
Yep.
one for the tiny stuff.
Yes.
And right now, we're not quite sure how they fit together into one grand, unified theory of everything.
Precisely. And that's where theories like quantum gravity come in,
Right.
trying to bridge that gap.
And I'm guessing there isn't just one theory of quantum gravity, is there?
You're absolutely right. There are multiple approaches to tackling this challenge.
Okay.
Two of the most prominent contenders are string theory and loop quantum gravity.
Okay.
Each offers a unique perspective on how to reconcile these seemingly disparate worlds.
All right, let's dive into these two contenders. String theory. That's the one where everything is made up of tiny vibrating strings, right?
Yes.
And what about loop quantum gravity? Didn't that one suggest that spacetime itself has a kind of granular structure?
Yes, you've got the basic idea. String theory proposes that the fundamental building blocks of the universe are not point-like particles,
Yeah.
but rather tiny vibrating strings.
Okay.
The different ways these strings vibrate determine the properties of the particles we observe, including their mass and charge.
Right.
And what's truly remarkable is that in this framework, gravity emerges naturally from the interactions of these strings.
So everything is made of these tiny vibrating strings. I'm trying to wrap my head around that.
Yeah.
But what about loop quantum gravity? How does that one explain gravity?
Loop quantum gravity takes a different approach, suggesting that space-time itself is not smooth and continuous as we generally perceive it,
Okay.
but rather quantized.
Yeah.
Imagine it like a piece of fabric woven from individual threads, rather than a seamless sheet. In this theory, those threads are loops of gravitational field lines,
I see.
and it's this discrete structure of space-time that could potentially explain the force of gravity.
So it's like the universe is a giant tapestry woven from these quantized loops, and the way those loops interact gives rise to what we experience as gravity.
That's an excellent analogy. The curvature of space-time, which we experience as gravity,
Right.
arises from the specific arrangement and interactions of these loops.
This is already blowing my mind, and we're just scratching the surface.
Yeah.
So we have these two leading contenders, both offering radical new ways of understanding reality at the Planck scale. Has either one emerged as the winner yet?
Not quite yet. Both string theory and loop quantum gravity are still under development.
Right.
Researchers are working tirelessly to refine them, test their predictions, and see which one, if either,
Right.
provides a more accurate and complete description of reality at this fundamental level.
So the race is on.
Yes.
Two theories, both aiming to unlock the secrets of quantum gravity.
Right. And the scientific community is eagerly watching to see which one comes out on top.
Absolutely.
But I'm curious, how do these theories affect our current understanding of the universe? What are some of the implications of a universe where space-time itself might be quantized?
That's a fantastic question, and it leads us into some of the most mind-boggling implications of these theories.
Okay.
If space-time is indeed quantized, it would mean there's a fundamental limit to how small an interval of time
Right.
or a distance can be,
Right.
like a smallest possible tick of a cosmic clock.
That's incredible. So it's not just that matter and energy are quantized,
Right.
but the very fabric of space-time itself might be made up of these discrete units.
Exactly. And this has profound implications for some of the most fundamental questions in physics and cosmology.
Okay.
For instance, it could potentially resolve the singularity at the heart of a black hole where our current theories break down.
I remember reading about singularities, those points of infinite density where all the laws of physics seem to go haywire.
Right.
That's right. Our current theories predict that when a massive star collapses, it forms a black hole with a singularity at its center,
Okay.
a point of infinite density and zero volume.
Okay.
But if space-time is quantized, there would be a limit, a quantum bottom, so to speak,
Okay.
preventing everything from collapsing to an infinitely small point.
So instead of everything being crushed into oblivion, there would be a limit.
Yeah.
A smallest possible space determined by the quantum nature of space-time itself.
Precisely. This quantum bottom might be able to resolve the singularity problem,
Okay.
smoothing out the infinite density and allowing for a more complete understanding of what happens inside black holes.
So quantum gravity might offer a way to peek behind the curtain of these cosmic enigmas. That's incredible.
It is.
And what about the Big Bang? Does quantized spacetime affect our understanding of the very beginning of the universe?
It certainly could. In the standard Big Bang model,
Hmm.
the universe starts from a singularity,
Yeah.
a point of infinite density and temperature.
Right.
But if space-time is quantized,
Okay.
there might have been a pre-Big Bang era governed by different laws of physics.
Okay.
A time before time as we understand it.
Whoa, a pre-Big Bang era. It's like opening a door to a whole new realm of possibilities.
Yes.
But these ideas are still highly speculative, right?
They are. But they highlight the profound implications of quantizing space-time. It challenges our most basic intuitions about the nature of reality
Right.
and opens up exciting new avenues for exploration.
This is also fascinating.
Yeah.
But I have to ask, are there any experiments or observations that could help us determine which of these theories, if either, is on the right track?
That's the key challenge.
Oh.
The Planck length is so incredibly small
Right.
that directly probing it experimentally is currently beyond our technological capabilities.
Okay.
However, there are indirect ways to search for evidence of quantum gravity effects.
Such as? What kind of evidence would we be looking for?
One promising avenue is to study the very early universe, particularly the cosmic microwave background radiation, which contains remnants of the Big Bang.
Okay.
If spacetime was quantized in the early universe, it might have left subtle imprints on this radiation
I see.
that we could potentially detect with advanced telescopes and observational techniques.
So it's like searching for cosmic fossils, remnants of the universe's quantum past.
Exactly. These imprints could provide valuable clues about the nature of quantum gravity
Okay.
and help us distinguish between different theoretical models.
It sounds like a daunting task, but also incredibly exciting. What other avenues are there for exploring quantum gravity?
Another approach is to look for violations of Lorentz invariance,
All right.
a fundamental principle in special relativity. This principle states that the laws of physics are the same for all observers moving at a constant velocity.
So if we find a situation where the laws of physics do vary depending on the observer's motion, that could be a sign of quantum gravity at work.
It could be. Some theories of quantum gravity predict tiny violations of Lorentz invariance that might be detectable with extremely precise experiments.
Okay.
For example, physicists are looking for variations in the speed of light, or subtle shifts in the energy levels of atoms
Right.
that could hint at the influence of quantum gravity.
It seems like the quest for quantum gravity is pushing the boundaries of both theoretical physics and experimental observation.
Absolutely. It's a truly multidisciplinary endeavor,
Wow.
requiring the collaboration of physicists, astronomers, mathematicians, and computer scientists
Right.
to unravel the mysteries of this fundamental force.
Yeah.
And who knows what breakthroughs lie ahead.
This deep dive into the Planck length has certainly opened my eyes to the vastness of the unknown and the incredible potential of these theories to revolutionize our understanding of the universe.
I agree.
It's clear that we've only just begun to explore the implications of a quantized reality.
I completely agree. And even if we never achieve a complete theory of everything, the pursuit itself is enriching, pushing us to think more deeply about the nature of reality and our place within it.
Well, we've covered a lot of ground in this first part of our deep dive.
We have.
We've explored the concept of the Planck length, delved into the mysteries of quantum gravity, and even touched upon the potential implications for black holes and the Big Bang. But there's still so much more to uncover.
Indeed.
Mm-hmm.
In the next part of our deep dive, we'll delve further into the specifics of string theory and loop quantum gravity, exploring their strengths,
Okay.
weaknesses, and how they might converge in the future.
That sounds fascinating. I can't wait to continue this journey with you. And to our listeners, thank you for joining us on this incredible exploration into the realm of the ultra-small. Stay tuned for the next part of our deep dive, where we'll continue to unravel the mysteries of the Planck length and the quest for a unified theory of everything.
Welcome back. Before we pause, we were discussing how both string theory and loop quantum gravity offer compelling frameworks for understanding what happens at the Planck scale,
Right.
that realm where quantum mechanics and gravity intertwine.
You know, as I was thinking about it during the break, it occurred to me that these theories are grappling with some of the most fundamental questions humans have ever asked, like, what is reality made of? How did the universe begin? It's awe-inspiring, really.
It truly is. And even if we never reach definitive answers,
Yeah.
the very act of asking these questions and exploring these theories expands our understanding of the cosmos and our place within it.
Okay, so let's get back to our two contenders for a theory of quantum gravity. String theory and loop quantum gravity.
Right.
They both offer fascinating perspective,
Yeah.
but they seem to take very different approaches. What are some of the key distinctions between these two theories, and what sets them apart in their attempts to unify quantum mechanics and gravity?
One of the most fundamental distinctions lies in their treatment of spacetime. In string theory,
Okay.
spacetime is the background,
Okay,
the stage upon which those tiny vibrating strings interact and create the particles we observe.
right.
It's a fundamental element,
Okay.
not something that emerges from other phenomena.
So space-time is like the canvas, and the strings are the brushstrokes painting the picture of reality as we know it.
That's a great way to visualize it.
Okay.
But in loop quantum gravity,
Yeah.
spacetime itself is woven from those quantized loops,
All right.
those fundamental building blocks we discussed earlier. It's not a fixed background,
Okay.
but rather an emergent property
I see.
arising from the interactions of these loops.
So in loop quantum gravity, the canvas itself is made up of tiny threads, and those threads, through their interactions, give rise to the picture, which is space-time. That's wild. It's like the universe is bootstrapping itself into existence.
It is a very intriguing concept, isn't it?
Yeah.
And this difference has profound implications for how each theory approaches gravity.
Okay.
In string theory, gravity is described by a specific type of closed loop of string called a graviton.
Right.
These gravitons mediate the gravitational force, similar to how photons mediate the electromagnetic force.
So gravitons are like the messengers of gravity carrying the force between objects.
Exactly. They're the force carriers, the particles that transmit the gravitational interaction.
Okay.
But in loop quantum gravity, gravity emerges from the geometry of those interconnected loops,
Right.
those building blocks of spacetime itself. The curvature of spacetime,
Right.
which we experience as gravity, is a consequence of the specific arrangement and interactions of these loops.
Okay, so in string theory, gravity has its own special particle, the graviton.
Right.
While in loop quantum gravity, it arises from the very fabric of space-time itself.
Exactly.
Both very different approaches leading to some unique challenges for each theory,
Yeah.
right?
Yeah, absolutely. For example, string theory requires extra dimensions
Oh,
beyond the 3 spatial dimensions and 1 time dimension that we experience every day.
okay.
These extra dimensions are curled up and hidden at scales smaller than the Planck length.
Hold on, extra dimensions. Now we're really getting into science fiction territory.
It might sound like science fiction,
Yeah.
but these extra dimensions are mathematically necessary for string theory to be consistent. They help to explain the diversity of particles and forces we observe in the universe.
So it's not that these extra dimensions are just added in for fun.
Right.
They're essential for the theory to work.
Precisely. The mathematics of string theory requires them to be there for the equations to make sense. Now, loop quantum gravity, on the other hand, doesn't require extra dimensions,
Right.
but it does face the challenge of explaining how the smooth, continuous spacetime we experience at larger scales
Okay.
emerges from the discrete, quantized structure at the Planck level.
So each theory has its own set of hurdles to overcome.
Yes.
It seems like the search for a unified theory is still very much a work in progress.
It certainly is. But it's important to remember that both string theory and loop quantum gravity have led to incredible insights and advancements in our understanding of the universe.
Right?
And who knows, maybe someday they'll converge, offering a single comprehensive framework that explains the nature of reality at all scales.
That would be amazing. A truly unified theory that encompasses everything from the smallest particles to the largest structures in the cosmos. But I have to ask, are there any practical applications for these theories? Or are they purely theoretical exercises for now?
While both theories are still very much in the realm of theoretical physics, they have stimulated new ways of thinking about cosmology, black holes, and the very nature of space-time. And the mathematical tools and concepts developed within these frameworks are finding applications in other areas of physics
Okay.
and even computer science.
It's incredible how these seemingly abstract ideas can ripple outward, influencing other fields and potentially leading to unexpected breakthroughs.
It really highlights the interconnectedness of knowledge and the importance of fundamental research, even if its practical applications aren't immediately apparent.
So we've explored some of the key differences between string theory and loop quantum gravity.
Yeah.
But you mentioned earlier that they might converge someday.
Right.
What makes you think that's possible?
There are some hints that these two seemingly disparate theories might be two sides of the same coin.
Okay.
For example, some recent research suggests that certain aspects of string theory, when viewed from a specific mathematical perspective,
Okay.
start to resemble the structures found in loop quantum gravity.
So it's like they're starting to speak the same language even if they're using different dialects.
That's a great way to put it.
Okay.
It's still early days, but this convergence is a tantalizing possibility,
Yeah.
suggesting that a more unified and comprehensive theory of quantum gravity might be within reach.
That's truly exciting, but I have to admit I'm still struggling to grasp the implications of a universe where space-time itself is quantized.
Right.
It challenges everything we think we know about the nature of reality. What would it mean for causality, for the flow of time, for the very concept of a beginning to the universe if space and time are not smooth and continuous, but rather granular and discrete?
That's a profound question, and it gets to the heart of why this research is so captivating.
Yeah.
If space-time is indeed quantized. Right. It would mean that there's a fundamental limit to how small an interval of time or distance can be. Imagine a universe where time doesn't flow smoothly like a river,
Okay.
but rather comes in discrete packets,
Yeah.
like frames in a movie reel.
Whoa. So instead of time being this continuous flow, it would be more like a series of snapshots, a cosmic stop-motion animation.
That's a good analogy.
Wow.
And this raises all sorts of fascinating questions.
Yeah.
Could there be gaps, moments outside of time,
Okay.
events that occur between the frames?
Right.
What would it mean for our understanding of cause and effect if time is not fundamentally continuous?
Mind-blowing. It makes me wonder if there's a smallest possible unit of space. Does that mean the universe is fundamentally finite?
Yeah.
Like a giant cosmic mosaic?
That's another intriguing possibility. It challenges our intuitive notion of infinity
Right.
and suggests that the universe might have an edge, a boundary, beyond which there is literally nothing,
Wow.
not even space or time.
This is all so much to absorb.
I know it is.
But even if we never directly observe these quantum gravity effects, just grappling with these concepts expands our understanding of the universe and our place within it.
Absolutely. It's a journey of exploration, a quest to push the boundaries of knowledge and unravel the mysteries of the cosmos.
Well, we've covered a lot of ground in this exploration of string theory and loop quantum gravity.
Yes, we have.
But I'm eager to delve deeper into the implications of a quantized reality.
And that's exactly what we'll do in the final part of our deep dive. We'll explore the potential implications of quantized space-time for black holes, the Big Bang, and even the very nature of reality itself.
I can't wait. To our listeners, thank you for sticking with us on this incredible journey into the realm of the ultra-small. Get ready for the final leg of our deep dive, where we'll venture even further into the mind-boggling world of the Planck length and the quest for a unified theory of everything. Stay tuned. Welcome back to the deep dive. We've been on quite a journey exploring the Planck length,
Yes.
delving into string theory and loop quantum gravity, and contemplating a reality where space-time itself might be quantized.
It's been a fascinating exploration, hasn't it? We've been grappling with some of the biggest questions in physics and cosmology.
Yeah, it's both exhilarating and a little bit terrifying
Right.
to realize how much we still don't understand about the fundamental nature of reality.
Yeah.
But even the questions themselves are profound and thought-provoking.
I couldn't agree more. It's the pursuit of these questions that drives scientific discovery and expands our understanding of the cosmos.
So let's dive back in. In this final part of our deep dive, I'm particularly interested in exploring the implications of a quantized reality. We've touched on this a bit already, but I'd love to go deeper.
Yeah.
What would it mean for our understanding of black holes, the Big Bang, and even the very nature of time itself, if space and time are not smooth and continuous,
Right.
but rather come in discrete packets?
That's where things get really interesting.
Okay.
If space-time is indeed quantized,
Yeah.
it would fundamentally change our understanding of some of the most extreme and mysterious phenomena in the universe.
Let's start with black holes. We talked earlier about how quantized space-time might resolve the singularity problem.
Yes.
Can you elaborate on that a bit more? How would a quantum bottom prevent everything from collapsing to an infinitely small point?
Imagine a tiled floor. You can't have anything smaller than one tile, right?
Right.
In a similar way, if space-time is quantized, there would be a smallest possible unit of space,
Okay.
sort of fundamental pixel of reality.
I see.
This quantum bottom would prevent the infinite density predicted by classical physics,
Okay.
because matter and energy couldn't be squeezed into a space smaller than this fundamental unit.
So instead of collapsing into an infinitely small point, matter and energy falling into a black hole would reach this quantum bottom,
Yes,
this smallest possible unit of space, and that would be the end of the line.
exactly. And this could have profound implications for what happens inside black holes. It might even open up the possibility of a balance at the center where matter and energy are repelled instead of being crushed into oblivion.
Wow, a bounce at the center of a black hole. It's like the universe's ultimate trampoline. But what about the information paradox? Doesn't quantum mechanics say that information can't be destroyed?
Right.
While general relativity suggests that everything that falls into a black hole is lost forever?
That's another puzzle that a theory of quantum gravity might be able to solve.
Okay.
Some physicists believe that information falling into a black hole might not be destroyed,
Right.
but rather encoded in subtle correlations at the event horizon,
Okay.
the boundary beyond which nothing, not even light, can escape.
So the information isn't lost, it's just scrambled and spread out across the surface of the black hole.
That's one possibility.
Okay.
And there are other theories that suggest the information might be preserved within the black hole itself,
Right.
perhaps in a form that we don't yet understand.
This is truly mind-boggling. It seems like every time we think we're getting closer to understanding black holes, new mysteries emerge.
That's the beauty of science. It's a never-ending journey of exploration and discovery.
Okay, let's shift gears and talk about the Big Bang. You mentioned earlier that quantized space-time might lead to a pre-Big Bang era.
Yes.
Can you expand on that a bit more? What would this pre-Big Bang era have been like, and how would it connect to the universe we observe today?
Imagine a balloon deflating instead of inflating. In some models of quantum gravity, the Big Bang might not have been the beginning of time,
Okay.
but rather a transition from a previous contracting phase of the universe.
Okay.
This pre-Big Bang era could have been governed by a different set of physical laws, and the Big Bang itself would represent a sort of bounce from this contracting phase
Right.
to the expanding phase we observe today.
So instead of starting from a singularity, the universe might have undergone a cycle of contraction and expansion,
Exactly.
with the Big Bang being just one phase in this ongoing cosmic dance.
Exactly. It's a fascinating possibility that challenges our conventional understanding of time and the origin of the universe.
These ideas are incredibly profound.
They're-
But I have to admit, they also make my head spin a little bit. It's
Yes.
like we're trying to grasp concepts that are beyond human intuition.
I understand completely. These are incredibly challenging concepts, but they also highlight the immense power of human curiosity and our drive to understand the universe around us.
Okay, so we've talked about black holes and the Big Bang. Now let's get even more fundamental. What does quantized space-time mean for our understanding of time itself? Does time really flow smoothly and continuously, or is it more like a series of discrete moments like frames in a film?
That's a question that has puzzled philosophers and physicists for centuries.
I bet.
If space-time is quantized, it suggests that time might not be this smooth flowing river we perceive,
Right.
but rather a series of discrete moments, like ticks of a cosmic clock.
So instead of time being this continuous, ever-present entity, it would be more like a sequence of snapshots, a cosmic flipbook.
That's a good way to visualize it.
Wow.
And this raises all sorts of fascinating questions. What happens between these moments? Is there a smallest possible unit of time? A fundamental chronon, so to speak.
Oh.
And what implications would this have for our understanding of causality and the flow of events?
Whoa. A chronon. That's a mind-blowing concept. It makes me wonder if there are limits to how precisely we can measure time,
Yeah.
just as there might be a limit to how small a distance can be.
That's a very insightful question,
Yeah.
and it highlights one of the key challenges in exploring quantum gravity. The Planck time, which is related to the Planck length,
Right.
is thought to be the smallest possible meaningful unit of time,
Okay.
around 1043 seconds. It's incredibly difficult to even conceive of such a tiny interval of time,
Yeah.
let alone measure it.
So it's like we're peering into the very fabric of time itself,
Yes.
trying to discern its finest threads. It's
Yeah.
a daunting task, but
Right.
also incredibly exciting.
It truly is. And while we don't have all the answers yet, the pursuit of these questions is what drives scientific progress and leads to new discoveries that can transform our understanding of the universe and our place within it.
Well, we've reached the end of our deep dive into the Planck length, and I have to say I'm walking away with more questions than answers, but that's okay, right?
Of course.
Because those questions are what keep us curious, keep us exploring, and ultimately keep us pushing the boundaries of human knowledge.
I couldn't agree more. The quest for a unified theory of everything is an ongoing adventure, and every new insight, every new discovery brings us one step closer to understanding the profound mysteries of the cosmos.
To our listener, thank you for joining us on this incredible journey. We hope you've enjoyed this deep dive into the Planck length string theory loop, quantum gravity, and the quest to understand the very nature of reality. Keep exploring, keep asking questions, and keep your mind open to the wonders of the universe. Until next time.